In this video, we will solve polynomial inequalities. We will graph them on a number line and write our answers in interval notation. So take a look at this problem number 5 here. We need 0 on one side, but we already have that. This is factorable. So basically what we're doing is we are considering the related equation x to the 4th power minus 81 equals 0. We're going to solve this equation to find the x-intercepts, you know, the zeros of this graph, and those will form our boundary points that will set off our interval notation. You'll see. So this is the difference of two squares. So we will definitely factor this as x squared plus 9 times x squared minus 9. Now, x squared plus 9 is unfactorable, all right? But x squared minus 9 can be factored. It has to be subtraction to be the difference of two squares. So x squared minus 9 factors as x plus 3 times x minus 3. So if I set each of these equal to 0 and solve, these two are super easy. So I'm just going to do them real quick. So I'm going to get x equals negative 3 here and x equals positive 3 here. Now if I set x squared plus 9 equal to 0, I'm going to subtract 9 from both sides, so that will give me x squared is equal to negative 9. Then I'm going to take the square root of both sides of my equation. All right, don't forget your plus or minus. So that's going to give me x equals plus or minus. Now this negative means it's imaginary, so that's plus or minus I radical 9. But the square root of 9 is 3, so that means x is equal to plus or minus 3i. Now our next step is to put these zeros on a number line. All right, so I've got negative 3, positive 3, then I've got these imaginary numbers. You can't plot imaginary numbers on a real number line. So we're going to wind up ignoring the imaginary ones. So on the number line, we're just going to do negative 3 and positive 3. Okay, so here goes the number line. So here I've got negative 3 and positive 3. So we need to decide whether or not we're going to do open circles or closed circles. So notice that we have less than or equal to. That means we want to include the values where the function equals 0. And that's what these are. The function equals 0 at negative 3 and positive 3. We will show that they are included by writing them as closed circles. Okay, so equal to negative 3, equal to positive 3, those are included in the solution. So we need to find out which of these zones have additional solutions. So we will discover that by doing test values. So we need a test value over here. For example, negative 4 is over here, so we'll check that out. We'll do a test value in here. So let's take a look at 0 is in here, so I'll just test out 0. Over here to the right of 3 is 4, so I'll use that. You don't have to use these exact values as long as you have a value to the left, a value in the middle, and a value to the right. Okay, so let's evaluate these. I'm going to use my TI-30XS multiview to help me evaluate. Okay, so grab your calculator, hit the table button. So I've got x to the 4th power minus 81. All right, for this kind of evaluation, I like to use Ask X mode. So I'm going to come over here to ask x and hit enter. So now I can type in exactly the values that I want to use. So we decided on -4, 0, and +4. So that's what I'm going to put in, -4, 0, and +4. Okay, so I can see the y values that I'm going to get. 175, -81, 175. Now, don't forget the original question. We want to know where the function is less than or equal to 0. So the question is 175 less than or equal to 0? Question mark. Well, that's a big old no, because it's greater than. What about -81? Is that less than or equal to 0? Question mark. Well, yes. All negative numbers are less than 0. And we've already answered this question. 175 less than or equal to 0? Obviously not. So this yes is reminding us that 0 was a solution. It gave us a true statement. So that means any value in this zone is going to end up being a solution. So we will show that these are all solutions by drawing a segment here. And that's it. There are no other yeses. So there are no other solution zones. Intervals. So let's go ahead and write our final answer in interval notation. Our solutions go from -3 to +3, including the endpoints. We show that the endpoints are included by using a square bracket. So we will go bracket, -3, and then +3 bracket. And that is my interval notation. All right, so that is it for problem number 5. All right, take a look at problem number 6. This is very similar, but we need 0 on one side before we really get started. So I am going to subtract 8x from both sides, and I'm going to add 20 to both sides. Now there are no like terms here, so I'm just going to wind up writing all of these in a row. So I'm going to wind up with 2x to the third power minus 5x squared minus 8x plus 20 is less than 0. Now we are going to start by solving the related equation, 2x to the third power minus 5x squared minus 8x plus 20 equals 0 to find the x-intercepts, which will be the boundaries of our solution intervals. So this is what we need to solve. There are two possibilities. I could put this in my calculator and solve it using synthetic division. Or I could try grouping. Now at a glance, grouping it looks likely to work. If you look at this first pair of terms, I see I've got -5 coefficient and I've got a 2. So that's -5 over 2. Keep that in mind. Now over here, if I do the same thing, I've got 20 and I've got -8. Now both of these are divisible by 4. Okay, so I'm going to have -5 over 2. Oh, look at that. It's the same thing. When these are the same, that lets you know that grouping is going to work. You know, assuming the variables are okay. Okay, so I'm going to do grouping, but then I will also quickly show you how you could do synthetic division as well. So grouping, you know what, maybe I'll do the synthetic division first, and then I'll erase it and come back and do grouping. Okay, so if I were doing this by synthetic division, I would type this function into my calculator. So I have 2x to the third power minus 5x squared minus 8x plus 20. Okay, and when I'm hunting for zeros, I need to be back in auto mode again. Okay, so here we are. You know what? I usually start at -10. I'm going to do that again. Okay, so starting from -10, I'm going to scroll down looking for zeros on the y side. The first one I find is -2. So that is a zero of the function. So I'm going to use that as part of my synthetic division. So I have -2, and then there's that 2, -5, -8, 20. So 2 times -2, so that's -4. That makes -9. -9 times -2 is positive 18. That makes 10. 10 times -2 is -20. Then I have 0. Putting the variables back in here, I'll just stick like this. So this is the constant, this is the x term, and this would be the x squared term. This -2 means that we have a factor of x plus 2, by the way. So far we factored it down to this. Probably this trinomial will factor further. So I am going to do my inner plus outer equals middle magic. So 2x squared is 2x times x. 10. 10 is either, when I look at 10, it's either going to be 2 times 5 or 1 times 10. So I'm going to start with the 2 times 5. I know better than to put the 2 here, because that would make a common factor, and there shouldn't be a common factor. So I'll put the 5 here and the 2 here when I do my 2 times 5. Now, inner plus outer must equal the middle. Inner, I have 5x. Outer, I have 4x. I'm trying to get a middle of -9, so that means both of these would have to be negative, which means both of these would have to be negative. A negative times a negative is a positive, so that works out. Okay, meanwhile, I bring down the x plus 2. So now I have factored it completely. All right, I factored that original problem. If I set each one of these equal to 0, I'm going to get my x-intercepts, my zeros. I will have the -2, which I already had, but I will have x equals 5 over 2, adding 5, dividing by 2, and I'll have x equals positive 2. So these are my x-intercepts. Okay, now I'm going to go back and do that by grouping, just because I want you to see how it's done. Okay, so I mentioned that grouping will work. So in grouping, you take the first 2 terms, you take the second 2 terms. The only common factor here is x squared. So I would pull that x squared out front. Okay, now if I divide both of these by x squared, here I'm going to get 2x, and then I'll just get the -5. Now on the second pair, I've got the negative, so I have to deal with that. But other than that, the common factor here is 4. So I will bring out a -4. Okay, so if I divide each term by -4, I'm going to get 2x minus 5. All right, dividing each of these by -4. Now I notice that I have the same factor twice. So 2x minus 5 is a common factor, so I'm going to pull that out front. All right, I'm going to undistribute it. I'm going to factor it out, and that's going to leave behind the green part, which is x squared minus 4. Okay, so I have a factor of 2x minus 5. I'm going to bring that down. But this x squared minus 4, that's the difference of 2 squares, and it factors as x plus 2 times x minus 2. If I set each of these equal to 0, I'm going to get 5 over 2, which is right here, -2, which is right here, and positive 2, which is right here. So you're going to get the same answers either way. So you just have to decide which is more comfortable for you and which way that you happen to notice. So it's time to put these values on a number line. We will put them on the number line as open circles because we just want the values where the function is less than 0. These are the values where the function is equal to 0, remember? So we need to leave them out, and we will show that by making them open circles. Anyways, here we go. So we have 3 values, 1, 2, 3. Open circle, open circle, open circle. All right, we have, okay, 5 over 2 as a decimal would be 2.5 because we're thinking 5 divided by 2, yeah? That is 2.5. So that is important to know as we place these points on a number line. So we're going to have -2 and then 2 and then 2.5 or 5 over 2. So that's what I'm going to do. So here I have -2 and here I have +2 and this is 5 over 2, which is 2.5. Okay, that's very important. Now, we need to pick test values in each one of these zones. So over here to the left of -2, we could choose a value like -3. In between these two, we could choose a value like, for example, 0. We could have done 1 or -1 as well. This zone is a little tricky because we need to pick something between 2 and 2.5. So, so just understand that, between 2 and 3 on a number line, what we have is, alright, so what we have is 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, 2.9, and then 3. That's how decimals work. We learned this back in like 2nd or 3rd grade. But sometimes we forget. So anyway, here we have the 2.5. Boom! That's a big highlighter. This is the 2.5 that we were speaking of. That's not a marker. Okay, this is that 5 over 2 that we've been talking about. So we need something between 2 and 5 over 2, or 2.5. So things like 2.1, 2.2, 2.3, or 2.4, these would be good values to use. So I'm going to use 2.3, for example. Okay, so f of 2.3. And over here, we just need something bigger than 2.5. So for example, f of 3 would work fine. You don't have to use these exact values, but you need something in each one of these zones. Now, we need to check the value of each of these and see if they are, in fact, less than 0, because that would make them a solution. So to do that, we're going to use our TI-30XS multi-view. Let's use the table feature. And you know what? We already typed this into the calculator a moment ago. So that makes it easy for us. So I'm just going to go ahead and use this. We're going to be using the ask feature, so it doesn't matter where you start. Alright, so I'm checking out -3 and 0. Just getting rid of that. We'll deal with that later. So We have -3 and 0. That's -55 and 20. Okay, so we've got -55 and 20. And again, we're trying to find out, are these values less than 0? All right, is this less than 0? And is this less than 0? Negative numbers are less than 0, so that's yes. Positive numbers are greater than 0, so this is a no. Okay, and now we're going to check out 2.3 and 3. Okay, so I'm getting -0.5 and 5. All right, so that's -0.5 and 5. And in each case, we're asking, are these values less than 0? That's negative, so yes, that's less than 0. This is positive, so no, that is not less than 0. That's greater than 0. Okay, so we end up with this pattern of yes, no, yes, no. The yeses show us where the solutions are going to be. All right, because we have a yes here, that means -3 is a solution, which means everything to the left of -2 is a solution. And we will indicate that by drawing an arrow in this zone. This is no, so 0 is not a solution, so none of these points are solutions, so leave it blank. 2.3 gave us a yes, a true statement, so that's a solution. That means all of these points are solutions. 3 gave us a no. That's not a solution, so nothing over here will be a solution. So this graph now reveals the solution set for the inequality. But in the end, we are supposed to write our solution set in interval notation. And looking at this arrow, it goes from -infinity to -2. All right, and we'll use round parentheses, which, like open circles, parentheses show that the end point is not included. And then we'll have to do a union, and here comes our second interval, which goes from 2 to 5/2. Again, parentheses for the same reason as the open circle, endpoints not included. And that's it. Maybe I'll put a box around this to emphasize that this is the final answer. And that's how you solve a polynomial inequality.